All right, guys, in our last section of Chapter 4, we're going to talk about solving equations. Not only logarithmic, but exponential equations as well. Okay. There's a few different ways that we can solve, a couple different ways we can solve logarithmic equations, or a couple different types of equations you'll see. So the first kind of strategy, okay, strategy number one, if we only have one log, if you take a look at example 1a, we have one log set equal to a number, okay? We can convert from log to exponential form. And remember, how do we do that? Log base A of B equals C will turn into A to the C equals B. Okay. Remember, we slide the base over, pop the constant into an exponent, and then the log goes away. Okay, that's where we get that A to the C equals B. Let's see how this would work in our solving logarithmic examples 1a here. All right. We have one logarithm set equal to a number, similar to what we have here. Okay, so let's rewrite it into exponential form. We slide the base, pop that constant up into an exponent, and we get to drop the log. And what's going to happen here, guys, is, I should take this final step, 2 squared. 2 squared is 4. This is an algebra 1 problem now. Okay, it's going to give you a quadratic function set equal to 0 and solve. Set equal to 0 and solve. Okay, x squared minus x minus 6 equals 0. We factor x minus 3, x plus 2. We get x equals 3. We get x equals negative 2. And what we need to make sure that we do is we need to check for extraneous solutions, okay? Need to check for extraneous solutions. If any of the x values that we plug into this formula, okay, this equation, would give us a negative inside the parentheses, okay? Negatives inside parentheses, those would be extraneous solutions. And we would want to throw out that answer. Let's check here. If I plug in a 3, we get 3 squared 9 minus 3 minus 2, that'd be 4. Plug in a negative 2, negative 2 squared is 4. Plus 2 minus 2 gives us positive 4. We're good to go for both of these answers. All right. The second thing is second strategy here is if we have multiple logs, a log on the left, a log on the right, as long as they are the same base, then we can just set those quantities equal to each other. All right, if you see at the left side and the right side are mirror images of each other other than what's in the parentheses. So if we have log base A of B, and that's equal to log same base A of C, then what's in the parentheses, those quantities must be the same. Okay. All right. In example 1b, that's going to happen here, but only after we condense. Okay. So can we take 2 logs of addition of the same base and turn it into 1 log? Yes, we can. That's going to help here. So then we would multiply the x and the x plus 1. We learned that in our last notes video, laws of logarithms, where 2 logs of addition turned into 1 log with multiplication between them. Okay. How would we do this? Well, we have the same log on each side, log of the same base, which means their quantities can just be set equal to each other. We would again, let's go ahead and solve here. What's going to happen, I'd love to show you one where we do end up getting extraneous solutions. We factor here, we're going to get 2 solutions of negative 5 and positive 4. However, this negative 5 is extraneous. Why? Plug that in there. Log base anything of a negative number, that's impossible. Why is that impossible? 5 to no power that ever exists is going to give us a negative output. Okay, so we're just going to go with x equals 4. This one would be extraneous. Right? C, we're not even going to do that one. That's just log base e, convert to exponential form, go from there. All right, let's talk about solving exponential examples. Okay. Now, as you can see here, we can't turn this 33 into the same base as we have over here. Okay. If we could, all right, if we have b to the a and b to the c, then we can set a equal to c. If our terms on the left and the right, our exponential terms, have the same base, then we can set their exponents equal. That will happen very infrequently. Okay? If not, let's take the log of both sides, similar to algebra. Okay? We can take square roots of both sides. We can square both sides. We can multiply and divide things on both sides of an equation. We can add and subtract, and we are allowed, with algebra rules, to take the log of both sides, as long as we're using the same base, and we're just going to take the log, base 10. Okay. So the first thing we need to do is make sure our exponential, our number to a variable power, is all by itself. Okay, so here it is not. So let's do example 2b, because it takes that extra step. I'm going to start example 2b by dividing by 2 to get my exponential by itself. And now I'm going to take the log of both sides. Okay. What happens, the reason we take the log of both sides is our log laws say that if we have a logarithm, we can bring an exponent out in front as a constant. That's something we learned in section 4.4. Okay. So when I take the log of both sides of this equation, all right, this exponent gets to come down as a constant. Basically, what taking the log of both sides does for us is it gets our variable down from the exponent. It's very difficult to solve for a variable in the exponent. Now, it's just another term, another constant. Okay? All right. There's a lot of different algebraic ways you can think about this, but I would start looking to get x by itself by dividing both sides by the log of 1/3. I get x minus 1 equals log of 7, and that's base 10 since it doesn't actually exist, and that's fine. And then I'm going to add 1 to both sides. We have solved for x. Our last step would be to plug that into the calculator. And we would get x equals negative 0.77, or approximately that. Be done and done. Okay. Let's think if this answer makes sense. Let's plug it back in. Negative 0.77 minus 1 equals 14. 2 to the 1/3 to the negative 1.77 power. Should that equal something around 14? Let's see if this makes sense. Well, if we took 1/3 to the negative first power, it would be 3, right? It would just flip the fraction. 2 times 3 is 6, less than 14. Okay. If we took 1/3 to the negative 2 power, it'd be 3 squared, because we flipped the fraction with the, then 2 times 9 is 18, which is like too much. Which means negative 1.77 should make a lot of sense for our, negative 1.77 as the exponent should make a lot of sense, meaning negative 0.77 as our answer should feel really good. All right, so a little recap of our notes here. Solving logarithmic and exponential equations, okay? In both forms, logarithmic and exponential, if we have the same log, we can set our quantities equal. Or if we have the same base, we can set our exponents equal. If that's not the case in our logarithmic function, and we just have one log set equal to a constant, let's change that to exponential form. If we have exponentials, where we can't get the same base on both sides, like I can't write 7 in terms of 1/3. 7 isn't like 1/3 to some power that's easily accessible, where then you could set the exponents together. When that's the case, let's take the log of both sides. That way our exponent will come down as a constant. And the rest is just algebra.